Hi everyone. Today we're going to be using what we've learned about experimental probability and relative frequency to predict outcomes. So make sure you write in your next clean page of your notebook 8.6 predicting outcomes. And we're going to calculate experimental probability from experiments. We can also call that relative frequency. And we're going to use experimental probabilities to make predictions when actual probabilities are not known. Okay, why do we learn this? Well, in real life, in manufacturing, you see this quite a bit, where they're trying to find how many defective products might be in a batch of things that are run. So in my example here, it says 1 out of 23 pairs of pants that are made, pairs of jeans, are defective. So how many will they expect to be defective in a batch of 300? Knowing this can help them with their figuring out their costs, how much to charge for things, because when they waste materials, there's a cost associated with it. And they also, if they start seeing too many, they might have some equipment failure that they might need to fix. So let's look at this example. It says 1 out of every 23 pairs of jeans are defective. We want to know, assuming this is going to stay constant, how many will be defective out of a batch of 300? Well, this is just going to be an equivalent fraction. 1 out of 23 is how many out of 300? It's actually a rate. One defective pair out of 23 pairs. So this is how many defective out of total. It's good to get in the habit of labeling, what you're looking at so that you know where to place your numbers. So if we're talking defective out of total, we have one defective pair out of 23 total. So how many defective out of 300 total? I'm going to put my variable x here. If you remember back when we did rates and ratios, cross products, this times this has to equal this times this. So 1 times 300, that's 300. I could write 1 times 300, but we know that's 300. Will have to equal 23x. 23 times x, which is 23x. Now we just have a simple one-step algebraic equation. Notice how all of this stuff comes back. Reviewing things we've done before. How would I solve for x? I'm going to divide both sides by 23. Now I am going to get a strange decimal number, but we're going to round it. So when I divide 300 by 23, I'm going to get about 13 pairs of pants will be defective in a batch of 300. It's not exact. It is an estimate. About 13 pairs and 300 will be defective. Does that guarantee that there will be exactly 13 defective pairs? No, it's just an estimate. It's a prediction. Let's look at another example. We have a toy company that makes robots. They inspect 200 robots at random. It's important that they say at random. If they pull them all from like the very first start of the run, the first 200 robots, if there was any sort of weird glitch at the beginning that fixes, they might not catch any. Or if something happens later in the run, they might not see, they might all be fine in the first 200. So it's good to pick out random ones. So when they did that, they found that 5 of the 200 did not work. So of my 200 robots, you can put an R for robots, 5 of them were defective. I could simplify that fraction. What would it be? We 1 in 40. But I'm going to keep it as is. We want to know how much that would be, how many would be defective out of 15,000 robots. Now we know a lot of different ways of solving equivalent fractions. We could say, what are we multiplying by from here to get to here? I'm going to stick with my cross product. So 5 times 15,000, 5 times, I'm going to use my x for times, I'm going to make it a star. 5 times 15,000 has to equal 200 times x. Just have to remember those cross products have to equal in equivalent fractions. This times this has to equal this times this. If I multiply 5 times 15,000, I'm going to get 75,000. Equals 200x. Again, after I get to this point, I have a simple one-step algebraic equation to solve. To get that x by itself, I just need to divide both sides of my equation by 200. And the number of robots I expect to be defective in a batch of 15,000 will be about, do my division, 375. I expect 375 defective robots out of 15,000 if I have 5 out of every 200. Remember, this is not a guarantee, it's just an estimate. It's a prediction of what we think will happen based on experience. Last, it says for a family with 2 children, there's a 25% chance that both will have boys. Now, we could make a tree diagram out of that. If you have a child, girl or boy, you have a second child, it could be girl or boy. So we have 4 potential outcomes according to this. Girl, 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 boy, boy, girl, boy, boy. And out of those 4 outcomes, 1 is boy, boy. So 1 out of 4 or 25% chance. So if we have a 1 out of 4 chance of having 2 boys, what is the likelihood of having 2 boys if you select 72 families with 2 children? It's important that it's 2 children. Otherwise, this whole thing wouldn't work. So, again, I could do my cross products. 1 family out of 4. How many out of 72? 1 times 72 is 72. 4 times x is 4x. You can divide both sides by 4. And the chance of having 2 boys, if you have 2 children, is 18 out of 72. Are there other ways you could solve this? Absolutely. How did you get from 4 to 72? You multiplied by 18. So if I multiplied my numerator by 18, I would get 18. So different ways you can solve it. But again, not guaranteed. It is an estimate. It is a prediction. These are the ones that always get students. At an arcade, Juanita wants to play a game 20 times. She has a 30% chance of winning. How many times can she expect to win if she plays it 20 times? Well, what does 30% chance of winning means? It means that 30 times, percent means out of 100. 30 out of 100 she expects to win. That's the same as 3 out of 10. 30%, of course. 3 out of 10. But that is her chance of winning. We want to know how many times she thinks she will lose. Well, if she wins 3 out of 10, how many would she lose? Well, she would lose the ones that she didn't win, so she would lose 7 out of 10. She would lose 7 times out of 10 games. But she's playing 20 games. How do we get from here to here? We multiply by 2. 7 times 2 is 14. She would expect to lose 14 of the 20 games. Could I have done the cross products? Absolutely. Put an x here, 10 times x, 10x equals 20 times 7, which is 140. Then I would divide both sides by 10 and I'd still get 14. Another way you could have done this is gone with her 3 out of 10. If she won 3 out of 10, then that means if she played 20 games, I could put a W here for 1. If she won 3 out of 10 games, she played 20 games, she would expect to win 6 out of 20. If she won 6 out of 20 games, how many did she lose? She lost 14. Could do it either way, but make sure you're calculating how many times she's going to lose. Those are those ones that get you, because you know that if it was multiple choice, 6 would be an answer on there, even though that's not the right answer. Always trying to trick you. So, that's it for today. If you have any questions, let me know. Talk to you soon. Maybe.